on to number 4 here to work through the first three. And for those who have completed, let's make sure that everybody has completed everything correctly though. Um, Number 2, and what were your answers for number 2? You asked to calculate resistance and inductance.
For the resistance, I got 110.85, and for the inductance, I got 0.265 Henry.
Ah, good. Who was that? I didn't see the person. So Chambers?
Yes, sir.
Oh, okay, good. So Camber, you agree with that?
Yes, sir.
All right.
I agree also, sir.
Okay. All right. Anybody disagree? I guess they won't say anything now.
And this is where we sample these features on. We made it bigger in the last one.
All right. What about number 3? They were to find line and phase voltage, reactive power, resistance, and reactance. All right. What was your line voltage?
461.88.
Okay. And phase voltage?
That was 266.67.
Okay. Anybody disagree with those? I guess that's unanimous, Mr. Mr. Campbell. So Chambers, how about you?
Same thing, sir.
All right. What about the reactive power?
This is what 16,702.72 VARs.
Okay. And the resistance?
5.87.
Okay, good. All right. And the reactance?
8.91.
All right. Very good. Very good. All right. So so for those who have completed those, you have you can look at number 4 here on the screen. So let me read it for you. Non-reactive loads of 10, 6, and 4 kilowatts are connected between the neutral and the red, yellow, and blue phases, respectively, of a 3-phase 4-wire system. The line voltage is 400 volts. Find the current in each line conductor and the neutral. All right, so you can work on that while the others work on question 1, 2, and 3. Is a device that converts energy, right?
Mm-hmm.
Yeah, so we're just looking at the basic things, right? What form of energy does it convert to another one?
Mechanical to electrical.
It converts
Electrical to mechanical.
It converts. You sure? So I hear 2 answers. So which one is it?
The motor convert mechanical to electrical.
Okay. All right. So you know that you have some you have a motor in your blender, right?
Yeah.
Huh?
Yeah.
Or in your fans? The ceiling fans? Huh?
Yeah.
Right. So how you make the fan work?
How about the fan work?
Yeah. How do you get it?
You plug it in, electrical.
You plug it in the electrical,
Yeah, plug it in. So
and then what happen?
current activate the motor, and the motor activate the blade.
Right. So the original source then to get the motor operating was what?
Electricity.
Right. And the mechanical action would be that rotating action of the motor that causes the fan blades to turn. So the motor converts electrical power to mechanical power. Right. So that power output that you see in the question is a mechanical power output, right? The output is mechanical. So what you need to do is to find the electrical power input. All right. And how can you go about doing that?
For electrical power input.
Right. From the information that you have in the question.
Yeah, the voltage. What again? You got volt and you have what? You have the mechanical power output.
Right. All right. So voltage would be on the electrical side. The power factor would be on the electrical side, right? Um, what else? What other information you have now that can help you find the input power, the electrical power input? So this is a question for everybody, you know. It's not only for.
There's a 90% efficiency, and you said that wouldn't.
So what is efficiency? What do we mean by efficiency?
The ratio of the input to output.
True.
So efficiency is not 100 if what the output is not what you put in. If you get less than what you input.
Right. Right. So what's the formula then for the efficiency?
Then the output to input.
No, say that again. I didn't get that.
Output over input.
Output over input. Right. So it's really power output, not just output, because you have voltage. Like in a amplifier circuit, you have voltage output and voltage input. That is considered to be gain and not efficiency. So when we talk about efficiency, we're talking about power in electrical engineering. We're talking about power output divided by power input. That will be the formula for efficiency. P out over P in. So if you have that, then you can work out what P in would be. Right, Mr. Atkinson?
Okay, yes.
Where can you go from there?
Plug in my formula.
Which formula?
The total power equal root 3 line voltage, line current, cos theta.
Right. All right. And then, so this is a, and then you can transpose to find the line current.
Yes, sir.
All right. So just go through with it now. 876G, do that too, and let's see if both of you get the answer.
Sir, I'm finally get this thing. I finally get
Oh, you got it.
94.34.
All right. Good. All right. So you're going to move. You're going to move on now to question 2, right?
Yeah, enough marking up doing now. Oh gosh. Couldn't figure it out.
All right. So remember, many times these things are just some step-by-step processes. Just remember what you would have learned before, and write down the information that you have and see how you can apply it to what you know. See how you can find your unknowns from your knowns. All righty. Time is running away. So Campbell, how question 4 coming along? Or Mr. Chambers?
I hope we're doing the right thing. For IR, we get 43.3 amps.
Okay, yeah, sound like you're doing the right thing.
And for IR and 25.98.
For IY?
Yes.
Yeah.
And then the other
At what angle?
minus 240.
No.
So is it 120, sir? Well, same thing. Get 120.
No, not 120.
I forgot to figure that out now.
What's the angle for AR?
0.
Oh, that is right. Yeah, so
We'll look at it again.
Sir, will all the angles be 0, sir?
no. Only for the red phase.
Sir, let us work together on this one.
Which one?
Number 2.
Alright.
Alright, so the line current is 5 amp, right? And the line voltage is 400 volts.
Right.
So couldn't which is also the field voltage, because it's delta, right?
Yeah, it is the phase voltage also.
All right. So couldn't you just find resistance by dividing the line voltage by the line current?
No. Can't find resistance like that. If it was a purely resistive load, you could do that. But from what they tell you, it's a coil, and the coil has resistance and reactance, right?
True.
So what would you be finding if you divide the voltage by current? And which current, by the way, you're dividing?
Sir, it would be the phase current you have to find.
You'd have to find the phase current, good.
And then find the impedance.
The impedance, very good. All right, so we have to be careful, Mr. Atkinson, we have to be careful with how we use the language. So it's not resistance now you're going to be finding. V over I is not resistance in an AC circuit, right? Unless so it is impedance.
True.
And only way it becomes a resistance if the impedance is purely resistive.
True.
All right. All right. What I'm gonna do is to bring up this solution because time is going, and I was hoping that we would have been further along and then working on question 4 by now. So yeah, quickly then for question 1, the Y connected motor 400 volt line voltage, output power 50 kilowatts, efficiency is 90%, or in terms of per unit 0.9. Per unit means that the units cancel. So output power over input power. Um, both are in kilowatts, so the unit would cancel. So it's just per unit. Power factor is 0.85. All right, so this is how the system was set up. I should have drawn a shaft here now to show you that the output power is the Pout is the 50 kilowatts. All right, then the formula for efficiency Pout over P in, and P in then is equal to that. And then we use the formula P in is equal to root 3 VLIL cos theta. So the line current is 94.34 amps. All right. So Atkins wanted to get to question 2. All right. So this is how the circuit tells us a coil, and in the information in the coil say it has resistance and inductance. So inductance would give you an inductive reactance, right? So this is the symbol for inductance and inductor, and this for the resistor. Yeah.
Would you need to draw like diagram in a test?
What do you mean? I don't understand you. Then how are you going to know what you're doing?
That's one there in the exam.
How are you going to know what you're doing? I need to be able to follow your work. So if you're not drawing a diagram, I'm going to be confused. And I'm just going to figure out, say, oh, you just probably copied this from somebody else.
Okay.
So you have to show me what you know. All right. Yeah, man, a diagram is important. It helps.
Sir, I have a question.
Yeah.
Sir, the impedance that you find, it's the oh, that is where I went wrong. I went and found the angle, sir, for the current.
Oh, okay. No
Yeah,
problem.
and then I divided it, so I got the complex value for the impedance.
Yeah, no problem. Good.
So I was saying you could use that for the resistance and the inductive the we call it inductive reactance, right?
Reactance. Right. Yeah, you could do that.
Then they use the formula for the inductive reactance to find the inductance.
Yeah. Yeah.
They could take that approach, but
Yeah,
sir,
man.
I don't get the value the 0.264.
All right. So All right. So what you have to do now is remember. All right. What I don't know. You find the line current, the phase current,
Yes, sir. Yeah, man, I got
the 2.87.
and then I found the angle.
So the
I
angle
found
would
the
be
angle
what?
based on the power factor. Based on the power
Right.
factor.
Yeah.
So it would be
So
the cos inverse of 0.8.
cos inverse of the 0.8. Right.
Yes,
Good.
sir.
Right. So it's supposed to be 36.87.
Right, 0.87.
All right. But
Well, I use
for the
basic
current
now.
now, right? For the current, it would be a lagging angle, right?
Oh, yes. Um. hmm.
All right. So you're finding it for IRY.
Yes, sir.
All right. Yeah, you could do that. And then so you're dividing VRY by IRY. So
Mm-hmm.
you end up with Z. So IRY would be at
I got one.
2.87 at angle minus 36.87. All right. So yeah, that can be
Yeah,
done.
yeah.
And then you'll get an angle for Z at as 36.87. So 138.56 at
Right,
angle 36.87. All right. So
right.
yeah, you could do that, which is basically how we have been kind of doing it. But I wanted to show you this way also. So we have the line current 5 amps, so we can find the phase current, right? And using this formula, Z equal to V phase over I phase. So this is a per phase impedance now. And we're just looking at the magnitude. That will be the 400 divided by the 2.887. And that gives you the 138.56. All right. And then we use this impedance triangle. And we know that this cos theta is equal to R over Z. Right? We know what theta is equal to, or cos theta is equal to 0.8. So R would be equal to Z cos theta. I think I gave it in the notes also. And so cos theta is 0.8. So R times 0.8 gives you the 110. All right. So this is another way of doing it. How you are doing it is okay. Nothing wrong with what you have did, except that you somehow seem to have lost your way somewhere. But the procedure is all right. XL now from this, sine theta is equal to XL over Z. So XL equal to Z sine theta. And sine of 37.6 times Z gives you 83.13. And we know XL is equal to 2 pi FL. So L is XL over 2 pi F. And that works out to the 0.265 from my calculation. All right. Any questions? So how you are doing it, Mr. Bruce, is okay if you want to say, all right, VRY is my reference, is angle 0, and we're looking at one phase, IRY. So IRY would be at the 2.887 at angle. Since it's a lagging power factor, angle minus 36.87. All right. So when you divide both magnitude and angles, now you get Z equal to 138.564 at angle 36.87, which is what we have down here anyway in the impedance triangle. And then from that now we can find R and L. Okay?
Yes, sir.
All right, good. Everybody else? So Atkinson? In this case, no, you didn't. Well, the question didn't ask you to do that. But if you want to have a good, that would be a good practice. So you always have a good picture of of what you're doing, how the current and the voltage relate to each other in terms of phase angles. All right. All right. Let's look at number three. The load connected to a three-phase supply comprises three similar coils connected in star. The line currents are 25 amps, and the apparent and active power inputs are 20 kVA and 11 kilowatt respectively. So find the line and phase voltages, reactive power input, and resistance and reactance of each coil. All right. So draw a circuit. We really don't have any details on circuit parameters or even voltage, but we know S, the apparent power is 20 kVA, and the real power is 11 kVA. All right, so somebody had asked about power factor. You can use that to find the power factor. Using the power triangle this time. So I've shown you the impedance triangle. We used it a while ago to help find power factor. So in the impedance triangle, power factor is equal to R over Z. In the power triangle, it's equal to P over S. All right. And you can see that it's a low power factor here, because you are basically putting what you think you are putting is 20 kilowatts, and what you're getting out is 11, not kilowatts, 20 kVA, because you're multiplying the straight voltage and the current by root 3, and what you're getting out is 11 kilowatts. So just 0.55 of what you put in, basically, or what you appear to put in. That's why it's called apparent power, because you would have think that this is what you should be getting out, but you're actually getting out less. All right. So we work out cos theta. We know that the power is root 3 VL IL cos theta. So from that we can find VL. Well, one other thing that we're supposed to find. So it's 11 kilowatts divided by the root 3 times the 25 for IL, and the power factor is 0.55. So VL works out to be 460, approximately 462. And V phase then would be VL over root 3, 266.67. All right. We can use the power triangle again to work out what the reactive power is. Q is equal to S sine theta. Look at the triangle. Q. So sine theta would be Q over S. So Q then would be equal to S sine theta.
Quick question.
Yeah.
Quick question, sir.
Yes,
when I
go
was
ahead.
doing this, I found the angle. Then I put in back the S at the angle in my calculator, and it gave me the A plus BI format, so I could find the Q. But that's
right.
not a real calculation. It's not a real
Yeah.
calculation. So would you lose mark?
Yeah, man, you can do that too. You just say the real part now is the P, and the imaginary part, the part that has the I associated with it, that would be the Q, the imaginary part. So yes, you can do that too. All right. So Mr. Bruce, when you had found the Z, if you had resolved it now into rectangular,
Yes,
you
sir.
would have gotten the R plus the JXL.
Right.
Right. So yes. So that is an approach that you can use also. Huh? So there are different ways of solving it. Well, you're actually using the triangle, you know. It just that's why I say no. It's very important that you understand your diagrams, because you're actually using the triangle. Even so the calculator is doing it for you. It's converting from polar, so it converting the 138.564 at angle 36.87. That would be a polar format, and you're converting it to rectangular. So when you convert to rectangular, now you get the R plus the JXL. So yeah, you need to understand what you're doing. So I understand what the calculator is doing also. Uh, yeah. All right. So it's basically the same thing we're doing here. All right. All right. So it's basically the same thing, and the same thing you can do for S equal to P plus JQ. So that can help you with that one also. Right. So you could find Q by just resolving this S at angle 56.53. You would get the P at 11 and the Q at 16.7.
Sir, for the
Yeah.
sine theta equals Q over S, shouldn't it be negative Q, sir?
No, it's actually um uh, since it's a inductive reactive, it's a positive Q.
Okay,
When
sir, thank
it
you.
is capacitive, it becomes a negative Q. All right. So yeah, you have to. So logging is what the current is doing, but that doesn't necessarily mean that is what the reactive power is doing. Right? For an inductive load would have a lagging power factor. But you see that the triangle shows that the power factor is positive, the angle is positive. Right? All right. All right. So 3 and 4 is here too. We have about 5 minutes. So well, less than our time is up basically. What I will do is ask you to work on those that you have not finished, and just email me your solution or your answers, and I can tell you whether or not you're and in a couple of days, maybe by Friday or so, I will post the solution.
Sir,
So I hope you.
look, for the last one, looking back at the question, I see non-reactive. So the current should be in phase with the voltage then, sir.
Right, that's right. That's right.
So,
Non-reactive means resistive, so no
yeah.
reactance in there at all. So once it's purely resistive, yeah, that's yeah. All right. So I'm happy that you saw that.
Sir, so you say it wouldn't be zero, sir.
All of them not zero. It only for the IR it will be zero.
So it would take the voltage angle.
Right. Remember, so the current is always going to be for a resistive load. The current is going to be in phase with the voltage. You with me?
Yes, sir.
So Vy is not at angle 0, and Vb is not at angle 0.
Yes, sir. Understand.
All right. All right. I will call it here. I will post this. I hope that you will actually try to work it out. Try to work it out, and then you can compare your answer. I'd said send me, but I will post this by Friday, so that I give you a chance to work on it. Some persons were able to do it overnight, so which means that others of you can do it also. And then Friday I'll post it. If you don't see me post it by Friday, somebody just send me an email. So solution for the tutorial for this week. All right. All right. So, good evening,
Okay,
everyone.
sir.